Good evening, everyone, and welcome to the 8th problem solving session of the course Fundamental of Semiconductor Devices NOC 24E02, hosted by NPTEL. Today is March 16. My name is Amit. I am a PhD student at ISC Bangalore. Quick summary from the previous session. First, in the week 1, we classified the materials based on their electrical conductivity given by this symbol sigma, and we find out a peculiar class of semiconductors as apart from metals and insulators, and they're peculiar in the sense that their conductivity can be tuned based on our requirement. And one of the special property we saw was the band gap in a semiconductor, and we saw that how it originated. You have to imagine that a large number of let's say when the atoms of a specific material, semiconductor material like silicon, are coming together, their orbitals tend to overlap, and finally what we have is we have bands of energies. Just a second. What eventually we see is a band of energies. So for instance, this is the upper band. Let's say this level is called EC, conduction band level, EV, and so electrons can reside either in the above EC or below EV, but not in between this forbidden energy gap, also denoted by EG. And also we can excite the electrons from one band to the other. For instance, if you can provide a photon or sufficient energy, electron will jump from the base of EV to EC. And converse is also true, that is, an electron can lose its energy and give away a photon and reach EV. We saw this in context of an LED, light emitting diode, right? And secondly, what we also saw that the electron which is there, let's say in the conduction band, is subject to periodic potential. Please remember, this electron is traveling in a lattice. It's residing in a lattice. It's not a free electron, so to speak. So it is subjected to a periodic potential, like something like this. So this is potential versus the position x, and we saw that, and when it's moved, this is the Ronick-Penny model. And however, when we draw the energy of this specific electron as a function of, let's say now, a wave vector. So this is energy and wave vector k, 2 pi by lambda. What we saw is that we can express this same conduction valence bands by something like this. They look somewhat parabolic in nature, something like this. So this is your conduction band, the top band, the bottom band is your EV, and this curvature that we see in EC can be used to determine the curvature of this conduction band gives the effective mass. This effective mass is a very useful construct in the context of semiconductor devices, because now we need not worry about this quantum mechanics, orbital overlapping, and so on. We can see whenever we come across the mass, all the classical equations we can use, just replace mass by this effective mass. That's all. And then we saw that how are these energies that I have drawn here, how are they dependent in 3D system. So we saw this density of states function dE was directly proportional to the square root of energy. So how many states are available essentially in this? If I draw, how many of these states are available, right? So this was given by root E. So density of state, number of states per unit energy per unit volume. Density denotes per unit volume. Electronic states in conduction band, holes in valence band. The second thing that we noticed was the Fermi function Fe. That is the probability that how many electrons will actually occupy these energy states. So this we saw was given by something like this, E minus EF. So for at E equal to EF, the probability of finding an electron at that energy level is exactly half, which is known as the Fermi level, denoted by EF. If E is greater than EF, then this will be greater than 1, and the probability will come out to be less than half. Finally, to find the total number of electrons, you simply do this density of states, that is the amount of electrons that are present, times the probability of finding the electron, EC. We integrate it from EC to infinity. Why? Because electrons will be residing only in the conduction band. And from this we obtained, based on some assumptions we had obtained, the expression eventually comes out to be something like this, where NC is effective density of states, right? Why this effective? Because you will likely find these many at the bottom of the conduction band, EC. Okay, and this was at equilibrium, that is, we are not applying any external bias or shining light and so on. Okay, but this is just for an intrinsic semiconductor. All this analysis was for an intrinsic semiconductor, that is, we are not adding any impurities or dopants as we call it. Now that there are two kinds of dopants that we can see. First is the donor. As the name suggests, it will donate electrons, so its level will lie somewhere over here. This is the, let's say, donor level ED. So what can happen is that now at sufficient energy, at very small energies in fact, what can happen is now these can donate electrons. So these donors are typically for a silicon. Let's say they will be group 5 elements like phosphorus and nitrogen phos in some cases, right? The other class of material, the other class of dopants is the acceptors. As the name suggests, they will accept the electron, so their level will lie, good acceptor level will lie somewhere over here, shown in green. So now the electrons can now jump from the valence band to this acceptor level. Note that these two levels are in the forbidden energy gap. Hence, now the number of, there will be a huge number of holes that can be created. Holes is nothing but the absence of electrons, and now these holes can help in the flow of current. Okay, in the case of the donors, so the electrons will be provided to the conduction band, and the electrons can flow in the conduction band and contribute to the current. Finally, we also saw that it's not always the case that these donors and acceptors are ionized. See, they need to be ionized. That is, either they have to donate electrons or accept electrons at very low temperatures. Let's say they have something called the incomplete ionization. Let's say below 100 Kelvin or something, right? And then we saw as we increase the temperature, we arrive at a state where all the dopants are ionized. That is, either they have accepted the electrons if they are acceptor types, or they have donated the electrons and thus become positively charged. A stage even comes if you further increase the temperature, and when that comes, what we have is we have an Ni square. So this doping just goes for a toss, and we will have essentially an intrinsic semiconductor. We usually don't want to go in that regime, but there are some applications where we want that. Finally, we talked about the Ohm's law. J equal to sigma E, as we call J is the current density, E is the electric field, and the traditional electrical counterpart which you have seen in your high school, V equal to IR. And how is this term sigma that we see is actually we denoted by this mu. Another concept, mobility concept we saw was how is the drift velocity. Drift velocity is nothing when you subject mobile carrier to an electric field, how it moves in the presence of an electric field. So when we drew this, it came out to be something like this. So at some point of time, some electric field, the drift velocity saturates. Okay, and the linear region called the low field regime, we called it as Vd equal to mu times E, right? Based on just these expression, we had obtained that this conductivity can be written as Ne nu, where N was the total electronic charge, total number of electronic concentration, E is the electronic charge, mu is the mobility of electrons. Similarly, their holes, it will be Pe mu P. For instance, like for the sake of clarity, let me call it mu N. Right, and the different scattering mechanisms as we saw. So, for instance, when the electron is moving, it can collide with a nearby atom, or if the atom is vibrating, or if there is, let's say, if it encounters now dopant, let's say, and then it will be attracted. So there can be two kinds of interactions, right? Two kinds of scattering mechanism. This was what we saw was the Coulombic, and this was what we saw was the phonon interaction, where it's just due to interacting with the vibrations, right? The other kind of transport mechanism of charge carrier, mobile charge carrier, is the diffusion. That is when you have concentration gradient, high number of electrons on one side, low on the other. We call the constant was D in this case, and we also saw that D and mu are related by something called the Einstein relation, D by mu equal to KT by Q. We had seen that. And finally, the total change of carrier density was due to drift and diffusion, as we have seen, and also due to generation and recombination. So generation when you shine a light, and recombination when you have a large number of electrons and holes in close proximity for a large amount of time, they can recombine, right? That's what the recombination means. So total current carrier density will depend on these four terms. This was, now we were equipped with the basics of the semiconductor physics, and we saw our first type of device called a p-n junction. Essentially, you bring a p-type doped material that is doped with acceptors and n-type doped with donors close together. You form a metallurgical junction, and naturally the electrons are huge amount on the right, so they'll diffuse to the left side, and what we saw was formation of a depletion region. That is depletion region where no mobile charge carriers are there, and we saw the band diagram used to look something like this. This is P side, this is N side. This band bending will happen in the depletion region. Depletion region means there are no mobile charge carriers. but there will be negative charge here and positive here. Now, this is an abrupt p-n junction. There are other flavors like p intrinsic n-type. P plus denotes high doping on p sides. In that case, depletion will be predominantly on the n side. This was under equilibrium. We saw how the charge profile looks. For instance, you can see negative, positive charge. The peak electric field will always lie at the metallurgical junction, which I'll draw here in the solid line, right? And we saw the depletion bit. We saw these expressions and the build. Naturally, if there is an electric field associated, there will be potential. That was we refer to as the built-in potentials. Then we can apply a forward bias. Forward bias means, let's say you apply to the p side, to the forward bias means to the p side of the device, you bias it, you connect it to the positive terminal of the battery, and then we can see that the built-in effective band bending reduces, and now the Fermi level in equilibrium, which was flat, right, because it's an equilibrium shown on this dotted line, now it will split. It will have quasi Fermi levels on the p side and n side, and if this barrier is lowered, then the carriers can be injected from the p side to the n side, the holes, and electrons from n side to the p side. These carriers will now diffuse across this reduced depletion region. They'll come to the p side, and the electrons will recombine here, and the circuit is complete. We had seen a good diagram depicting the various contributions of electron diffusion current, hole diffusion current, electron drift, and hole drift, and so on. Next we talked about was the p-n junction in a reverse bias, which is again, as the name suggests, now p side will be connected to the negative terminal of the battery. So in this regime, we saw that the very less amount of current flows, and this current flow is predominantly due to the drift of the carriers, which has somehow reached the widened depletion region. In this case, the depletion region is usually very wide, and the depletion region is usually very wide. What can happen is that these charge carriers can gain sufficient amount of kinetic energy, because if you recall that your typical Newton's third law of motion, that v square equal to u square plus 2as. Let's say u is 0. So if you travel a long distance, right, your velocity will keep on increasing. A is constant because the electric field will depend on the applied potential. Let's say we keep it fixed. We reverse bias, we are keeping it fixed, whatever the magnitude is. But as you travel more distance, the kinetic energy of the electrons will increase, right? And the kinetic energy increases, then what can happen? They can knock out other electrons, and this will give rise to a chain reaction, and we result in something called an avalanche. A huge amount of current can flow in the avalanche breakdown in reverse bias. Zener breakdown happens when we have p or n highly doped. So in that is more likely of a tunneling phenomena. So it was something like this. So this is your p-n junction. This is heavily doped, so you can see that the electrons which are here in the valence band can now simply tunnel to the other side. The band-to-band tunneling we have also seen in context of another device called the tunnel diode, in which we analyze this device in forward bias. So, but a Zener breakdown also is a p plus n plus junction operated in reverse bias, which is helpful for voltage regulation. The other applications we saw was, as I mentioned just now, the tunnel diode, in which we saw the IV characteristics look something like this. First, the current increases due to tunneling, then current reduces due to the fact that tunneling has started to reduce, but the typical drift current has not increased that much. And if you increase the bias further, the p-n junction forward bias, now the diffusion mechanism will now kick in, not the drift. Here we have something called a negative potential, which is a unique phenomenon of the tunnel diode. And other devices which we talked about were LED, photodetector, and solar cell. This will be coming in the next 3 lectures, 9, 10, and 11, I believe. Finally, we saw another type of junction called the Schottky diode, which is a metal semiconductor junction. We saw what are work function, electron affinity. The two types of contacts we saw are rectifying and non-rectifying contact. This is, in fact, non-rectifying contact was of a very particular significance. So when I say that we make a contact with the P side of the terminal, it needs to be ohmic. It cannot be playing any other role. When we want to collect a metallic wire with the P-type junction, we want it to be so that it does not behave, it does not create its own effects. We don't want that. So for that we want non-rectifying contact, means ohmic behavior. And we saw that the mechanism is thermionic. The current conduction mechanism is thermionic for a Schottky diode. Then the next device, we increased the level even further, and we had now 3 terminal devices, the NP and BJTs, emitter, base, and collectors, the 2 flavors, NPN and PNP. And we saw why the doping of the emitter has to be the highest, and the doping of the base has to be the lowest, as well as base has to be thin in order to avoid the recombination effects. And we saw when we bias a BJT, that is the emitter base bias and the base collector bias, we can have 4 different regimes. If you recall the table, the forward active, where emitter base is forward and base collector is reverse, that's a forward active mode. The other cutoff was when both were in reverse bias, and so on. And finally, based on our analysis focused mostly on the forward active mode, in which we saw various terms like the emitter injection efficiency. That is how so emitter injection efficiency, if you recall, was IEN over IEN plus IEP, right? And the base transport factor is essentially how many electrons are getting recombined with this p-type base so essentially that was your ICN over IEN. And the current gain beta we eventually determined, and there was other factors alpha also, so it was IC by IB. These are terms we had talked about and some of the semiconductor physics. Finally, in the last session, which I believe is the core of, or rather the heart of this course, is the MOSCAP metal oxide semiconductor capacitor. We saw how it's formed, that is the formation by which I mean that we have a metal, then we have an oxide, and then we have the semiconductor, and these are the two terminals. We apply a bias here. We typically call this the gate. Today we'll come to know why we call this the gate. This was the semiconductor, this was usually ground. We saw the two flavors, NMOSCAP, PMOSCAP, depending on the doping of the substrate. So when it's a p-type semiconductor, we saw it's an NMOS. The 4 regimes that we saw, I'll just quickly go through the revision in a bit detail. We saw the onset of strong inversion, that is the inversion we had defined, the case when the minority carrier concentration at this interface exceeded the majority carrier concentration in the bulk, right? So in this case, let's say it's a p-type semiconductor, we said N at surface is greater than or equal to P in bulk, the holes in bulk. So that is when we had the onset of strong inversion. There were mathematical expressions involved. We saw that threshold voltage depends, how it depends on substrate doping, the metal choice, because metal semiconductor work function also comes to the picture, as well as the gate dielectric, its dielectric constant, as well as the thickness. And then a core concept called the high frequency and low frequency curves, capacitance voltage curves, which we had seen for an ideal MOSCAP. So they look, first we had the accumulation, and then you have the depletion, and finally in your inversion, so this is C versus V, right? So this is your high frequency. And for low frequency, what can happen, because the electrons will get sufficient time, what you have is something like this. So this was Cox, this level was Cox. We had seen that how HF, how high frequency and low frequency CV curves differed. And we also discussed the non-idealities, like the metal semiconductor work function difference can arise, and there can be, the oxides need not always be perfect. And to carry on with my discussion that I've talked about, the ideal MOS capacitor that we saw that the metal semiconductor Fermi levels were the same, and there were no, so this was a perfect oxide, and there were no trap charges, for instance, in the oxide, which it seemed was not the case, right? And the 4 regimes that we saw, when you don't apply any bias, so we what we call the flat band, because EC and EV are flat, and you can see EF is closer to EV, so this is a p-type semiconductor in the bulk that I'm talking about. Finally, if you apply, let's say, some negative potential, what will happen is that this majority holes there will get attracted to this. So this is, we refer to as the surface. So on the surface, you can see is that the EF is closer to further EV as compared to the bulk. This means, if you recall the expression, P equal to NV exponent of EV minus EF over KT. So the EV minus EF has reduced on the surface, so the whole concentration increases. That's why you call this accumulation. However, if you apply negative bias on this, what you can do is you will repel away the holes, right? If the holes are repelled away, what essentially is going to happen is something like this. The bands will bend in a different direction as compared to this. Other thing you can see at the surface itself again, EV minus EF, this is EV. EV minus EF at the surface is more than in the bulk, right? So just a second. So this must always be negative. Yeah, so EV minus EF is more negative in this case, so this exponent will be smaller, right? And hence you will, what you see, you will start approaching the, this is EI, the dotted line is EI. You will see that the material at the surface is losing its p-type behavior. However, if you keep on increasing the gate bias even after depletion, what you will see is at the surface EF is now closer to EC, while in the bulk EF is closer to EV. What we have done is now at this surface, this has now become n-type, electron rich, while the bulk is still p-type, right? This phenomena is known as inversion. You just by applying a bias at the gate, you have altered the nature of the semiconductor, right? So this is, and as I'm saying, this inversion is the core of the device that we are going to talk about today. Just to summarize, this is from the previous class itself. A MOSCAP is said to be inversion when is said to be inversion? We have seen that it's said to be inversion when the minority concentration, this is the surface, and just look at the concentration of electrons here. Concentration of electrons, the minority concentration, because this is a p-type material in the bulk, minority will be n-type and majority will be p-type, and the bulk it's p-type. So as I told, n surface when it becomes greater than or equal to p bulk, that is what that's what we refer to as inversion, right? So when the minority carrier concentration of the surface equals or exceeds the majority carrier concentration in the bulk, right? This is what we had talked about. Okay, 1 second. Right, and these are some of the expressions. So for instance, phi f was something this level. This is what we had defined as phi f. Phi s is essentially the nature of bed bending. So you see EI bulk minus EI surface. So this is what we had seen as phi s. So essentially the strong inversion we refer to as phi s is 2 phi f. That is, the bent has bent not just intrinsic. So to make it intrinsic, phi s should be equal to phi f, which we saw in the depletion diagram in the previous slide. However, we want to make it n-type. How much n-type? The strong inversion is said to have happened. This is the condition of strong inversion, by the way. Strong inversion is said to have happened when phi s equal to 2 phi f. That is, it is as much n-type at the surface as it is p-type in the bulk. So because the bending on this side and this side is the same. Okay, right. So a problem related to the MOSCAP. So in this we have an ideal MOSCAP has a boron doping concentration of 10 to the power 15 per centimeter cube in the substrate. So we'll assume this is a silicon material. In fact, it's given later that it's silicon, and we are doping it boron. Boron, if you recall, is a group 3 element, right? And carbon, silicon is group 4, so it will have a p-type. So we are doping p-type. P-type silicon substrate is what we have for this MOSCAP, right? So thus EF will be closer to EV in the bulk. We are talking about only in the bulk. Now what we have is, and let's say, let me also write that Na is 10 to the power 15 per centimeter cube. When the gate voltage is applied, a depletion region of width 0.5 microns is formed. So here, since it's the p-type, we know we have to apply positive gate bias to repel the holes. So this is the depletion region that has formed. This depletion region width W is given as 0.5 microns. Okay, with a surface or channel potential of 0.2 volts. So this phi s has been given as 0.2 volts, and we have given the permittivity of the free space, and for silicon and silicon dioxide is also given. What we are required to find is the peak electric field in oxide region, electric field here. How do we do that? So what we do know is that let me draw this in a physically how it look like. So this is the metal or the gate, this is the oxide, and this is the semiconductor, p-type silicon, and this is grounded. right? This semiconductor is grounded here, so this means this interface over here, sorry, this over here is grounded, right? Okay, so now what we can see is the extent of band bending, or which we also known as the built-in potential. The built-in potential is being given equal to us as 0.2 volts, because this is the surface we are talking about. The metal, the oxide semiconductor interface was given to us as 0.2 volts, right? So this is 0.2 volts, is the built-in potential, and we also know that the profile, right? If I draw the electric field versus, let's say, x, okay, and this is what I'm calling it as x equal to 0. Okay, so it will look something like this. Why this discontinuity over here? Because please remember, the displacement vector has to remain constant. That is, this is oxide and this is semiconductor. We had seen that epsilon oxide times electric field in oxide must be equal to epsilon silicon times electric field in silicon. I am assuming there are no interface charges, so which is where this term ideal MOS capacitor comes into the picture. Okay, so we are required to find the electric field in oxide.
Once again, sir, one doubt.
Sorry?
One doubt, sir.
Yeah, go ahead.
On the oxide side, how electric field is negative, sir?
Okay.
Because of voltage is E is the minus of del cross B. That's the phenomenon.
Okay, let me just see if it's positive or negative. I was just drawing from the PN junction because of the familiarity, but let's see. Let's just analyze that. Is it negative or is it positive? I was just trying to emphasize this discontinuity here, but let's just be correct. Let's try to find out whether the electric field will be positive or negative. So what we have here is that on this interface we have a positive potential, right? And here the potential is 0. Okay, so so if I recall, E equal to minus dV over dx, right? Minus grad V. So if I try to do that, so let me say that so let's call this interface V metal. So V metal minus, and let's say this is 0 because I mean this is indeed 0, divided by some negative x minus x metal minus let me call this 0 itself for the sake of it will be essentially some negative number. That's all I mean to say. So what we'll have is that this will get cancelled, so it will have V metal, which is positive, by X metal, which is also positive. Yeah, so electric field will be positive. So what I've drawn here is wrong. This will not be like this. You're correct. The electric field will be positive. Something like this. This discontinuity I don't know, but the nature, but it will be something like this. So electric field has to go down to 0 at this interface. This is essentially W. This is essentially W, and this is your oxide, and here you will have some so metal will be equipotential surface. So yeah, it will look something like this. So what I'm interested in is only finding what's happening over here. Okay, so let's try to do that now. So the built-in does that answer your query whether it's positive or negative, the magnitude of electric field? Does that answer your question? Whoever had asked?
Yes, I answered. Correct, sir. Thank you.
Okay, fine. Thank you for asking. Right. So now let's go ahead. So what essentially we need to find out is electric field of silicon. How do we do that? It's very straightforward. So the electric field of silicon, the potential is coming due to this facet over here, this triangle that you see. So built-in potential. So essentially, if you integrate E dx, you will get the delta V. So what I am going to, we need to just to integrate this curve E versus X curve. So it's a right angle triangle. It will be half times E times silicon. Okay, this value that I have been referring to as, it's E silicon, and this value is, let me use a different color, just a second. So this value is what I am referring to as E silicon, that is electric field, peak electric field in silicon. This value I am referring to as E oxide, that is peak electric field in oxide, and this will happen at this junction, the semiconductor oxide junction. And yeah, so coming back, so it will be the area of this right angle triangle will be half times base into height. Height is electric field of silicon times W. This should be equal to 0.2. So electric field of silicon, the peak electric field will come out to be a second. Yeah, so 2 into 0.2 divided by the depletion width, which was 0.5. So the units will be volts per micrometer, because this is volt here, and the W I am putting in microns. So this will be 4. Yeah, so it will be 4 into 0.8 volts per micrometer. So this is electric field in silicon. Let's put this number here. Epsilon oxide is given to us as maybe 4, I guess. Yes, 4 times E oxide equal to, this is given as 12. Electric field in silicon is given as 0.8. So 4 times 3 is 12. So electric field in silicon will be 2.4 volts per micrometer. So the electric field in oxide is higher, and as we see, it's not continuous. It will not be continuous because there is essentially a jump. The material has changed. So this is just like your refraction that we talk about, that you must have seen in optical physics, because the interface changes. And so this is the answer. So the answer would be 2.4 volts per micrometer. Okay, so is there an option? Yeah, there is an option. So one key thing that I want to point out here, not just in the context of MOSCAP, in the context of MOSFET also, this dielectric is of primary importance. Apart from the fact that it has to be nearly ideal without any trap charges and interface traps and so on, we want this to be as good as possible, and the electric constant plays a key role, because electric field, or the value of peak electric field, is determined by that itself. Okay, so while designing that, we'll come across a problem later today where we revisit this role of dielectric again. In the last session also we had talked about this, by the way. Okay, so MOSFET, as the name suggests, metal oxide capacitor, FET, is the heart of it is the MOS capacitor. Okay, so let's just we had talked about in the last session what a resistor means. The potential difference between the two terminals, the left and right, will determine the current flowing between them. So this is an analogy of a pipe, and the water is there. If the pipe is level, that is the potential on both sides is same, no water and thus no current will flow. However, if you tilt it in such a fashion that the potential on the left is higher, that is, it is raised high, the water will start to flow from left to right. Similarly, if you tilt the pipe in the opposite direction, that is, the right terminal is the higher potential, the water will flow from right to left. Similarly, similar case for current. Transistor we had talked about. In this case, a third terminal will control the current flowing between the two other terminals. So we have this terminal left and right, which on your screens, and let's say a middle terminal which is slightly raised, so only a small amount of water can flow. However, if I lower this middle barrier, by the way, left and right barrier still remain the same as the earlier case, right? More amount of water can flow, and if I raise the barrier, it can so happen that no amount of water flows. So what happening essentially is that the third terminal, in this case, the third terminal is this. Let's call this. This was a BJT diagram, so let me call this base itself. So this base is determining the current flow between the emitter and the collector, right? We had seen this in the, I think, 2 or 3 sessions, 2 sessions back. Okay, the other type of transistor is a field effect transistor. So these type of This transistor we had seen was BJT, bipolar junction transistors, because it depends on the junctions and their the bias that we apply naturally, and also on the respective dopings. The other is FET, field effect transistors, as you see over here. So this is just the schematics that I have drawn here. The two flavors as we are talking about, the NPN, right? Emitter is N, base is P, collector is N. So this is an NPN BJT, and this is a PNP BJT. And you can also see, I have not denoted the doping here, but you can see the area. So for instance, collector is always has a much larger area, and you see the thin base. So the base, because the electrons have to travel from the emitter to the collector. And on the bottom we have is a FET, right? So FET, just forget about the source and drain for now, and you can clearly see the rest looks exactly like a MOS capacitor. We had this terminal, the meta terminal here, then the oxide which is riding on the silicon. So for a P-type silicon we had noticed, and now we have given this terminal a name called the bulk terminal or the body terminal. Okay, so if you recall, when we inverted that, so for a P-type silicon, on this interface, oxide semiconductor interface, an inversion layer of electrons can be formed, right? And if you can connect these electron layer to these other two terminals, the source and drain, and you apply a potential across the source and drain, the current can flow. So just to repeat, first you form an inversion layer by applying let's say in this case a negative potential, VG negative, let's say large negative rather, and you form an inversion layer denoted in red here, and what you will have is you have a layer, and this is connected to this N plus region. So this is also electron rich. This layer is also made up of electrons. However, now what you do, let's say you apply this zero potential, and let's say you apply, let's say 2 volts. So now you have an electric field in the lateral direction also, from left to right, and these electrons can now flow, right? So there's a higher potential, so the electrons will be attracted from source to drain. So source will provide electrons and they'll travel in this direction. The other flavor naturally is when your body or the semiconductor is N-type silicon. So when we have an N-type silicon, in that case, if you apply a sufficiently positive voltage, right, positive voltage, you can have an inversion layer, this time of holes, like, right, hole inversion layer. Why? Because the substrate is N-type, so you can have an hole inversion layer. And again, if you have source and drain as P-type, now you have a continuous layer of holes. Again, if you ground the source and you apply, let's say, some positive potential here, 2 volts, again the holes can flow. So the inversion layer is being formed by the effect of electric field where it's applied by the gate, right? So this is controlling how much amount of inversion mobile charge carriers will be there, and then you can change depending on the value of drain and source, respective value of drain and source, that whether you want to flow a current or not. But the main cause of this inversion is the electric field of gate. Hence these are called field effect transistors, as compared to the BJTs we had talked about 2 sessions earlier. Okay, and this is at this point of time it's a good question to, just because depending on their applications, for instance, predominantly in FETs are one of the mostly used devices in consumer electronics, for that matter. So and here we just want to talk about, I know I have not introduced the drain current concept, but I had given a hint that when you apply some drain bias, current can flow between source and drain, which was the case when we saw in emitter base, right? You have forward bias the emitter base and reverse bias the base collector junction, and you will have your BJT in forward active. So we'll talk the FETs in a bit more detail, but let's just let's still just talk about this phenomena here. So first let me talk about the BJT current, or in this, to be more specific, the collector current, that how it behaves when we increase the temperature. Okay, so if you recall, and I'm assuming the forward active, okay, and I'll assume that all the other things are there, that the base doping and dopings are good enough so that it's an ideal forward active. Okay, so its expression looks something like this. Okay, and this is nothing but a reverse saturation current. um, I'm not able to recall the terms here, but I do recall it was dependent on the diffusion constant and the Ni square, and inversely proportional to the doping of the base. Okay, yeah, it was something like this. Okay, so now we are interested in finding the temperature dependence. Okay, so all the other terms were temperature independent. In fact, the base, the doping also is temperature independent. The only temperature dependent terms are the diffusion constant and the and your intrinsic carrier concentration. Okay, and how does the diffusion constant depend? So we know d by mu equal to kt by q, right? So d is equal to, let's say, kt by q times mu, and mu, we have seen that if you are operating above room temperature, goes as T to the power 3 by 2. Sorry, reduces as T to the power 3 by 2. Okay, so essentially we can say that D goes as T to the power minus half. The first term, the diffusion constant. What about Ni squared? So if you recall, in I think the second or third session, we had talked about that Ni square is in fact, if I recall, was T cube and then exponent of minus Eg by kt. Okay, so what you do, if you increase the temperature, right, if you increase the temperature, this term reduces, and this term reduces, this term increases, exponentially rather. Okay, because when you increase the temperature, this negative term goes down, right, and the negative term goes down means essentially Ni square rises, and this rise is exponential. Okay, so if you put both of these terms here, so we rise that it's an exponential rise, and this is a square root decrease, square root fall, which will dominate naturally. This will dominate, the exponential rise term will dominate. So Is, and mind you, these other terms will I'm not taking into account the kt term over here. In fact, that will also play a role, but here if you can see, the t cube here itself is there. Okay, essentially it will be VBE minus Eg over kt, and VBE we have typically seen comes out to be around 0.7 or something, 0.7 volts, but Eg is 1.1 or 1.2, right, for a silicon. So essentially this term will turn out to be negative. So overall if you see, this will be an exponential increase. The cumulative effect of diffusion constant with square root fall, Ni which rises exponential, and even if you take into account this picture, exponential rise will still dominate. So Is, or rather in this case Is, and thus IC will also rise exponentially. Okay, so we can see that there will be an increase in BJT collector current. This is the correct option. Now let's talk about the second device, which is the FET. So FET is what they have is, you have to trust me on this. We'll see that the FET, I'm assuming so this, if it's a P-type semiconductor, we had seen what we form is the NMOS, right, NMOSCAP, and thus NMOSFET also. So ID will be mu n C ox W by L Vg minus Vt whole square by 2. This is the expression in saturation, right? So we will derive this expression, don't worry, but just trust me that this is true. So let's talk about the dependence, the temperature dependence again. Cox is a constant, this will not change. WL is a constant, it will not change. Vg is the bias that you are applying, that will not change, when it's independent of temperature. The two terms there, which are here, is mu n and Vt, the threshold voltage. So mu n, as we had seen, is reduces by t to the power minus 3 by 2. It goes, mu n goes as this. Vt slightly decreases, but that is more or less a logarithmic log decrease. the decrease is logarithmic. When we'll come to the expression for Vt a few slides later, then you will be able to see that what I'm talking about. But for now, we'll see the Vt decreases logarithmically. Okay, when this decreases logarithmically, so this means Vg minus Vt will increase, but again logarithmic, and this is a 3/2 dependence. So this dependence will naturally win over the logarithmic. So whatever gain in current you can have with the decrease in Vt, this will be more than compensated by this decrease in the electron mobility. Okay, so thus we observe that practically the drain current, this is drain current in saturation in MOSFET, decreases as we increase the temperature, and this is predominantly due to the fact that mobility has decreased. Even though the threshold voltage has decreased, it's not sufficient to compensate for the decrease in mobility. Okay, so what we have is decrease in MOSFET drain current. Again, there's more than one correct option, so I'm attempting this since I'm confident I know the nature, how collector and the drain current behave. Okay, right. Now this question pertains the polarity of inversion layer in a MOSFET, not MOSCAP. In a MOSFET, the polarity of the inversion layer is same as that of. We had talked about this in context of the MOSCAP. So MOSCAP, we know that, let's say this is p-type silicon, for instance. For a p-type silicon, the inversion layer which will be formed here will be of electrons. Inversion layer of electrons. We saw that in the sense that because first this has to be depleted. Depleted means holes are pushed away, and if you still apply a negative potential, if you still keep on applying a negative potential, what's going to happen is that positive potential. If you keep on applying a more positive potential, holes will get repelled away, and the electrons will be collected over here, and this will be, because the substrate is p-type and this layer is rich in electrons, we have an inversion. So we have, for a p-type substrate or a p-type, in this case bulk or body, we have an inversion layer of electrons. So again the same thing will happen here, the inversion layer of electrons over here as well. So inversion, these electrons are minority in bulk, right? The polarity of the inversion layer is same as that of minority carriers in the bulk. So also it has the same polarity because we want to modulate these electrons that are here. The source and drain have to be of the same polarity, otherwise they'll result in recombination, right? So what we have is the source and drain have to be of the same polarity as that of the inversion layer. So if the inversion layer is electrons, right, then it has to be, the source will have to be rich in electrons. So the majority in substrate, majority in the source and drain will be the same as inversion layer. Inversion layer is same as majority in source. This is incorrect because this has to be, the inversion layer is the minority in the substrate, right? And source and drain will have to be the same. They are the same polarity. So this is n plus type, this is also n plus type. This plus again is here to make, if you recall, so that there is no so that this is heavily, so this is more or less to determine, this is more like, behaves like a metallic contact, right? So that there are no other secondary order effects that are coming to the picture. This is heavily rich in electrons because these have to supply the electrons as well. So we don't want the concentration of them to be decreasing just by the creation of the inversion layer. So these has to be sufficiently highly doped. That's why this plus sign. Okay, so till this point of time, we had talked about the basic structure of a MOSFET and the various terminals that it has, the 4 terminals in this case. I think I missed the term, yeah. So actually this is wrong here. The Vg will not be negative here. Vg is positive because we are talking about the p-type silicon. So in order to form an inversion layer, the holes have to be repelled. Okay, and similarly on the other side here, what we have, the Vg has to be negative, not positive. So Vg has to be negative. Also the terminals. So typically we see in the BJT it's a 3-terminal device, NP, N, P, and P. It's MOSFET is a 4-terminal device. Gate, a source and drain. This is very analogous to your emitter, base and collector. However, the 4 terminals also there is the bulk or body. We'll see if it plays a role, or it's just a it's a useless terminal. We'll see sometime later. Okay, so the next problem that we have over here pertains to, so right, so consider the following statements. The n channel MOS transistors or N MOSFETs are faster than PMOS. Second thing is that surface field effect is the operation principle of MOSFETs. So let's first talk about the first point. What about which are faster? So if you recall, the current is, for instance, when I'm talking about the P silicon, so it will have an inversion layer of electrons. This is an N MOSFET. So I'll write mu n C ox W by L. Again, I'm talking about in saturation. Okay, it comes out something like this. Also for this, it will be mu P C ox W by L. Let's say Vg minus Vt. Why I'm putting the absolute terms here? Because these are negative. Please remember, this gate has to be negative in order to cause a depletion in the n-type silicon. Thus, to have the same effect, to remember the same expression, we just put the absolute terms. Okay, so let's just forget first of all, we'll say that Vtn and Vtp, they have the same magnitude. Let's not worry about that. And we are applying the same Vg, W by L, C ox, everything else is the same. So the only thing that is different in IDN and IDP is the mobility. The mobility of electrons in NMOS. This is your NMOS. This is your PMOS. The only thing that is different is the mobility of their respective charge carriers. And we know that mu n is greater than mu p. The mobility of electrons is larger. This essentially stems from the fact that holes have, in order to jump from one place to another, there needs to be another hole, right? That fundamentally reduces the hole mobility. So mu n will always be greater than mu p. This means that IDN will be greater than IDP, provided all other things are constant, right? So if this is the case, and we are talking about fast, right? So faster means this is essentially your rate of transport of electrons, because remember, this is over time, dq over dt, right? So rate of transport of electrons is higher as compared to rate of transport of holes. So this means if you want to transport electron from here to here, turn off the channel, turn on the channel, NMOS will be a faster device, just because of that it can carry more current, and the more carrying of more current is predominantly coming because the electrons can travel faster, so it can switch on and off faster. The electron, if it's here, if you have to form the so switching will happen when you change the drain bias. So drain bias you reduce, you will switch it off. Okay, so those things, the electrons, since they can travel faster, or even from the inversion layer to the back to the substrate when you change the gate voltage for the switch operations, that is better. So in that case, NMOS are faster, so that is correct. Second, surface field effect is the operating principle of MOSFET. We have already talked about this. We need to form an inversion layer here, and that inversion layer is formed predominantly to the electric field that is being applied by the gate along this surface. So on this surface, this is a 2D surface, by the way. We'll see in the next slide what do I mean by that. So this field effect is essentially what is driving this whole device. So this is also correct. So both statements 1 and 2 correct. So this is what it is. Now we'll get into the, I'll take a pause here. If you want me to repeat something, ask a doubt, please go ahead, because next we'll talk about the operation of a MOSFET. There are different regimes, as we had seen for a BJT, like depending on the bias of their different junctions, as well as what we had talked about was different biases, and the predominantly biases that in the case of BJT. For MOSCAP we had again different regimes depending on the voltage of the gate. Similarly we'll see that, but if you have any doubts, please feel free to ask. Okay, let's go ahead and talk about the operation of a MOSFET. So, so this is an N-type MOSFET as we are seeing over here. Sorry, this is a P-type silicon. So an inversion layer will be formed over here. That inversion layer will form when you have sufficiently positive gate bias. Okay, because first depletion and then inversion. So that is a knowledge that we have from the MOSCAP. Okay, this is a 3D schematic of this same device that's drawn here. So let's just try to understand one by one. You have this big P-type substrate, which you see at the bottom, P-type substrate, same as this. Then you have the source and drain contacts, which are N plus in nature, which you are seeing source on the left over here, and you have the drain here, right? Then what we have is then we have the oxide. So you see this is the oxide written over here. This is the oxide layer, which I'm pointing now, with the thickness Tox. And finally what we have is the metal. So you see this gate metal, which is over here, which is in the green, in the gray region. So this is the gate metal. So now we have gate, the 4 terminals you can see, gate, source and drain, and source and drain are N plus types, just like this. And this is the P-type substrate. The other key thing to notice is that the width of the device, W. So till at this point of time, even in the case of MOS capacitor, we had never talked about this with W. Essentially, the higher the width, everything else remaining the constant, the current increases. The current through to, because now, so just think of it as this in parallel. So one layer of electrons here, one layer immediately behind, and so on. So the wider the device is, the more the current it can carry. Right, this is the length of the device. From actually, it's the oxide is actually from L drawn, what you see over here, and L effective is the total length which the electrons will travel, and they travel from source to drain, right? And this LD is nothing but your overlap. So we tend to have that when we this is the design from this book, and this is more or less from a realistic device. Okay, so hence you see some other terms, many other terms, and many other like this, how they are making this contact. Okay, we'll not go into that, but so this is the diagram that we keep on repeating, but this is just a schematic to show that in 3D how it looks like, right? And in this, for a MOSFET, we'll be talking about the 3 regimes. Okay, the 3 regimes that we have are switch off or off. Second is the linear regime, and the third is the saturation regime. So there, the word saturation, the way we define saturation in FETs is distinctly different that we define in context of BJTs. So I also get confused, so I try to remember through their output characteristics. Okay, and that's what I would suggest here also. Again, this formula is just taken directly from what we had in MOSCAP, right? So this first 2 terms, if you recall, were from this is also known as VFB, flat band. This first term was coming to the metal semiconductor work function difference, and let's say this QOX. This QOX by COX was due to the trap charges that we might have inside this oxide layer. So this was the oxide layer, this is your semiconductor, and this is your metal. From MOSCAP we had seen that, and the other 2 terms, so this was coming from the band bending or the strong inversion, let's say, and this term was the depletion charge, because inversion will happen only after the depletion. We had talked about these terms in the last session, just revisit them for more details. Okay, but this is where I'll build up from. All right. Okay, so let's just first talk about the first regime of operation, which is the linear. And actually first one is cutoff. I'm not talking about the cutoff yet, because it's fairly simple to identify, essentially, when there's no inversion layer. So let me say it here right off. So cutoff is when Vg is less than Vt, and for all my discussion I'll be talking about this NMOSCAP or NMOSFET rather, on a p-type silicon substrate. Okay, Vg is less than Vt, and until otherwise said, this terminal is grounded, just like we had seen in terms of the MOSCAP. But here there are two other terminals. So usually source is the one that is grounded, but here I'm explicitly saying the body is always grounded, right? And source is also usually grounded. We'll see that. Okay. Okay, so moving ahead then, now let's talk about the second regime, which is the linear. Okay, same diagram. I would like you to notice the x, y, and z direction. So x is let's just first denote this. So this is a p-type substrate which is grounded. Okay, source, which is the n plus, also grounded. Drain, we'll apply some potential here. What potential we'll see? N plus. And this width I'm not showing, I'm just showing the cross section in this case, which is the minus z direction. So you can see the z over here, and so the metal will lie somewhere over here. The gate is over here. So gate is modulating the field in the negative y direction. You see the y direction over here. It's modulating in the negative y direction. So so in the gray region, what you are seeing is the depletion region. The gray color, this color, denotes the depletion, and the dashed region what you are seeing, just a second, yeah, so and then the dashed region what you are seeing is the so this is a bit misleading. It's induced depletion, not depletion but rather inversion, and the dashed region that you see over here is your just a second, okay, so this blue region that you see is the inversion layer, which will be of electrons, since this is a p-type substrate. The dashed region that you see is the depletion region, okay, due to the fact that we are applying some potential. What potential? You can clearly see if the inversion is there, you have to apply a positive bias. Okay, some assumptions, because this inversion has already formed, we'll be operating at Vg greater than Vt. What is Vt? Vt we had already seen over here. This is the expression, I'm not writing it again. This is the Vt that we have. So we are operating at a gate bias which is greater than Vt. So the inversion layer is already there. And Vd, this Vd, because VDS, why VDS? Because we are measuring everything with respect to the source. So I'll also say it's VGS rather. This is a reference electrode. Okay, VDS is small, so that Q inversion is uniform. You see this inversion block that you see, the blue block that you see, it's a rectangle, right? For now we'll see VDS is very small. By that I mean, let's say it's 0.1 volts, very small value. So that there is a negligible electric field. There is some, but very small electric field in the x direction. So x direction is from source to drain. Okay, right. So as I said, what is the value of Vg? So as I've said, Vg, first it will be phi ms, right, minus q ox by c ox. This is the flat band that you need to achieve, right, minus q depletion over c ox to cause depletion, which you see in the dashed region, and then finally you have 2 phi f. This is due to the inversion, right, and then finally minus qi over c ox. This is the extra conversion. You will be able to notice that this is nothing. This is q ox here. This is nothing but your Vt, right? So Vg is greater than Vt. That's what I've written here. Vg, how much higher? By this amount. Okay, it's higher because Qi is negative. This is an inversion layer of electrons. Okay, so what I'll do is that I'll rewrite this expression here. I'll write Vg minus Vt equal to minus Q inversion over C ox, right? And from this I can write Q inversion is equal to C ox times Vg minus Vt, just the cross multiplication, nothing else. Okay, what will be the current? Current will be Q inversion times, say, okay, I'm just writing the magnitude here. Okay, just to be very clear, I'm just writing the magnitude of the inversion charge, which is the blue region over here. So Q inversion times, so current, what will the current? And see, why area? Because the C ox that we write is we typically normalize with respect to area. Okay, so what will be the area of this device? Area will be the length of the device, which is given by L here, and the width of the device, which is into the plane of the paper, negative z direction. So area will be L times W. Fair enough. What will be tau? Tau I can write as whatever the distance this has to travel, right? Tau is the time taken for the electron to travel from source to drain, because that's where the lateral electric field. So Q inversion, it just creates this block of charge, the blue region. The current will now, the electrons will travel now from, because for higher potential, from source to drain. How much time it takes, right? Very simply, time will be length upon speed. Distance upon speed is time. What speed? Drift velocity. Now drift velocity, which drift velocity? In the x direction, because that's what we are interested in, right? And we know drift velocity is in the low field regime, Vd equal to mu e. In the revision today we also saw that Vd equal to mu e. Please remember, Vd I'm talking about in x direction, this direction between source to drain, right? And why I can write this as low field? Because remember, we are applying a very low potential over here. Or alternately, you can just assume this is a very long, what we call them is the long channel MOSFET. This L is large, very large, so that we do not enter into that regime as of yet. Okay, so L by mu e. E is the electric field, again in the x direction, this direction. So electric field will be simply, since this field, this I am applying very low potential, I can simply write L by mu Vd by distance. Electric field is Vd by distance, so this will come out to be L square by mu Vd. Vd is the drain bias, VDS, let's say. Okay, let's put all of these terms here. So I can write now, so I'll write in a different color. Now I can write that I equal to Q inversion is this Cox Vg minus Vt times area is WL, divided by tau. Tau is this L square by mu VDS. One L gets cancelled. What I get is Cox, mu will come out on this side, Cox W by L, one L remains, right? Vg minus Vt times VDS. Current I have obtained as this in the linear regime. Okay, now let's try to plot this, how it looks like. So this is ID, it's also known as ID or IDS versus VDS, right? Because these are the two terminals across which I'll remember, gate voltage is as the knob. I told you, the barrier which increases or decreases, right? ID versus VDS is the output characteristics, like when you draw I versus V of a resistor, right? So how does it look like? So I versus V is a straight line, I versus VDS is a straight line, right? Let's draw this. It's a straight line for a given value of Vg. So let's call this line is Vg1. Let me draw another line now, okay, for a different Vg, and let's say this is the line that I get. This is corresponding to Vg2. This will again be a straight line because ID is strictly proportional, still proportional to VDS, but its magnitude will be lower because why? In this context I am saying Vg2 is less than Vg1. So you see, we will get different straight line different slopes of these straight lines, and how much, and this makes sense when you apply a lesser Vg, still higher than Vt by the way. Both Vg1 and Vg2 are still higher than Vt because an only inversion layer is formed. However, Vg2's magnitude is lower than Vg1, but that means is that you are piling up less inversion charge over here. Okay, you are piling up less charge, so naturally there will be lesser current, right? And hence a lower slope. Okay, I'll repeat, Vg2, since Vg2 is less than Vg1, what you are essentially doing is you're piling now lesser amount of inversion charge. and if there is lesser amount of inversion charge, there will be less current, because essentially current is nothing but q over t, right? And so q, when you have lesser amount of charge, and assuming tau does not change time constant, so what you will have is you have lesser current. Okay, so in this case, what we had done, just the takeaway from this is that you can operate a MOSFET in linear region, provided first you have VGS greater than VT, and second you have very small VDS, such that this block, the blue block that we see, is uniform. It's a perfect rectangle. And second thing what we notice is that just by changing the value of VG, you can change the amount of resistance that this device will provide, because the slope is just the conductance and then thus the resistance. So by changing the slope, you can change the resistance this device will provide. This means this can be used as a resistor, this device, in the linear region. Okay. Second regime is the saturation. But so now from linear regime we'll try to go into the saturation. Okay, and that's what this that's what I'm trying to denote here. Okay, so what we have here is something called the gradual channel approximation. So let's try to understand what that means. I'll contrast with the previous diagram. So what you see here is that the inversion layer was a perfect rectangle, so was the depletion region. Okay, here what you will see is that that's not the case. Why is that not the case? So let me first just clarify the assumptions and the different terms over here. So again, as before, the x direction is from source to drain, right? And this is the on the left is your source here, this is our drain here, right? And the electrons will travel from source to drain. This is a p-type semiconductor substrate, so electrons will be in the inversion layer, which you see over here, right? We'll come to why its shape looks like this, and we have applied a positive potential at the gate high enough above VT, right, above VT, such that inversion layer is formed at every point here, 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 here. At all these points you can see an inversion layer being formed. At all these points across x, from x equal to 0 to x equal to L. So this is x equal to 0 and this point is at x equal to L. Throughout this you can see that that's happening. Okay, right. And the second thing what I have so that is that. So now what I'll do is that at any random point over here, right, what I'm doing is I'm making some assumptions. We call this point as V channel, the potential of this channel, in the x direction again, that's why this term denotes x, is Vg minus Vx. Why Vg minus Vx? Because the potential here that we have is Vx. In the previous case that was not, we did not state it explicitly, because why? This Vx was more or less flat. Remember that Vd we chose as 0.1, here Vd is higher, which is saying that Vds is large enough is that Q inversion decreases gradually towards drain. Now the question arises, okay, first we know that Vd is greater than Vs. Vs is typically what we ground. Okay, and Vd is now, let's say I'm putting at 2 volts. So just some values. Vd, let's say I'm putting at 2 volts. Okay, earlier it was 0.1. So Vds is now large enough. So now what's going to happen is that just look at the extreme left and extreme right. On the extreme left, what you have is the potential you are applying is Vg, and that Vg has to drop in the oxide, right? Again, recall the expression that all the gate potential that you are applying has to first go into the flat band to make the bands flat. Second, it has to go into the depletion, then the banding, and then the inversion charge. So there are 5 components. Okay, so if I have this Vs equal to 0, the potential at this terminal equal to 0, now more of it will go towards the inversion. On the other hand, on the right side, what we have this Vd terminal also there. Now what's happening is that I'll draw it over here. So this is our drain, N plus drain, right, and this is the P. I am applying a positive potential at P, and this I have told it's grounded. Just look at this N plus P terminal. N plus is connected to some positive potential of, let's say, 2 volts. P is grounded. This is a reverse bias junction. This is an N plus P. What's going to happen? The depletion region, this is the source. This is also grounded. Depletion region over this N plus P junction, the source N plus P junction, will be narrow. I'll draw it in a different color, purple. This will be narrow. I'm just drawing the depletion region, forget about the gate. It will look something like this. This is an N plus P junction, and it's reverse biased, and we know in N plus P, depletion region lies predominantly on the low doped side. Here the depletion region will look something like this. I'm exaggerating it, but that's intentional. So this is the depletion region. This again is also the depletion region on the source. Now what you are doing, so the depletion region that is here has now, is not just due to the effect of the gate, because gate is applying a vertical electric field in the negative in the y direction, but the depletion region will be cumulative of the electric field due to the drain as well as due to the gate. Okay, and hence what we see, this depletion region is enhanced on the drain side, which you're seeing in this cross section. This depletion region of the source is smaller, so the more component of the gate can now go for the inversion, because this now does not this is depleted enough. Now it can simply start the inversion. However, on the drain side, the depletion region is wider, right? So more charge essentially you can say stored there. The less charge will be in terms of inversion charge. That's what this denotes. These two regions. That's why we call it a gradual channel approximation, and we assume that this is a linear decrease in the, let's say, inversion layer thickness, so to speak. Okay, so by gradual channel approximation, we are assuming that the voltage, or rather the inversion layer charge, is decreasing gradually, or to be more precise, linearly from source to drain. And the primary reason that is arising because the depletion regions between the source and substrate and the drain and substrate are different. Okay, so more component is there of the depletion region on the drain side. That's why it looks like this. But still, inversion is still happening on the drain side as well. So inversion is happening throughout. It's just that the extent of inversion charge is smaller on the drain side. That's it. Okay. And as we saw in the previous slide, Q inversion was Cox Vg minus Vt. Why? The Vx term was not there. The channel potential. Channel potential we assume was, because Vd was so low, we're assuming that it's negligible as compared to Vg and Vt. Here it's not the case. Vx can be significant enough as compared to the Vg and Vg minus Vt terms. So hence Q inversion looks something like this. Again, the old expression, the current will be Q inversion times area, because Cox is typically normalized with respect to area over tau. Tau is again your so area we can simply see is W into L. That does not change. Time constant, I'll write it here. Time constant is given by this. Let's just see. I'm talking about only this infinitesimal area, this area. What is this area? Delta x or dx, this length, delta x. Delta x by Vd, the drift velocity. Simply the time taken to transit the electron, this delta x length. Delta x will not change. Vd, again assuming we are in low field regime, by mu e. So mu is the mobility of the electron here, and E is the electric field that it has experienced in this region. What is the potential over here? No, the channel potential it's over here is Vx, and E equal to dV over dx. Again we are talking about the magnitudes here, so don't worry about these signs. Okay, so this is the time constant, time taken for the electron to transit at this interface in the inversion layer. This is the time it will take. Now what we'll do, we'll put all these terms that we had talked about in this expression, in the expression over here. So Q inversion is Cox Vg minus Vx minus Vt times area is W dx. The length that you want to traverse is this dx or delta x, hence w dx. The time taken is we have given by this expression. So now what you will see, again this is the current that is crossing this region. Please remember, we are only interested in this region for now. Okay, so what will it come? So let's see if there's some terms that are cancelling out. So these two terms get cancelled out. One second. Yeah, so these two terms will get cancelled, right? And what I'll get is mu will come up again. So mu C ox W over dx Vg minus Vt minus Vx times dVx. This is the current only in this region, mind you. And KCL says that, so whatever current, if charge is not being stored here, that means we have achieved the steady state. So when I integrated this, so we take dx on the other side, I dx will change from 0
dx will come to the numerator.
Dx will
come to numerator.
So on the other side it will come to the numerator in this side. This will u C ox W, and then we integrated Vg minus Vt,
on the same side, dx will come up.
dx will come on the same side? No, I don't think so. See, the mu will come up, then dx has to be in the denominator. This dx and this dx got cancelled, right? The only dx that remains is this. So mu, this is upon, and this is also on the denominator. So this whole term mu dvx over dx comes in the numerator, which I have written mu dvx over dx, and then I'm cross multiplying. Dx will not come in the numerator. This dx got cancelled, which was in the numerator. This got cancelled, and this is still in the denominator. So Vg minus Vt minus Vx dVx. So where dVx varies when x equal to 0, Vx is 0. Vx is the channel potential, which means we are at source. We are at 0. And when x equal to L, we are talking about Vx as Vds. Okay. I is constant, as I told you. The current will not change when you are traveling from left to right, because KCL, we are not storing any charge here. Right, so all the current which has been inducted from source will remain the same throughout the length of the channel. So I can then write running out of space. 1 second. I times L equal to mu C ox W. Vg minus Vt is a constant with respect to dVx, right? So this will come Vg minus Vt times Vds, first term, and the second term is Vx dVx. So this is like x dx. So it will be x square by 2. It will come out to be Vds squared by 2. This is I times L. Again, if you bring L on the other side, so the final expression will come out to be Id mu C ox W by L. L has come downstairs. Vg minus Vt times Vds minus Vds whole squared by 2. This is the final expression of current that we had arrived at. Just to summarize it again, what we are doing here is, again we are assuming that throughout the channel we are in inversion. We have entered the inversion. So this you see at every point of time over here, the inversion layer is still there. The only question is that when we talk about gradual channel approximation is that the inversion layer is not uniform. It's tapered. And the reason it's tapered is because the potential Vd is high enough that the more contribution is being caused by the depletion layer as compared to the inversion layer. On the source, the depletion contribution is much lesser as compared to the inversion layer. Right? And this comes from the fact that because after you cross the inversion of strong threshold, or let's say when you cross Vth, right, all the extra charge that you're building up will be stored in the inversion layer, right, which is not the case for the drain side, because the depletion region is widened, which is shown over in this schematic on the extreme left of our screens. And the rest is just simply the exercise that we had done before. that in this infinitesimal region, what will be the inversion charge? It will be capacitance, it's the oxide capacitance times the potential. So what is the potential? Vg is the total potential applied, Vt is the potential that has been caused to onset of strong inversion, and we deduct Vx because it is the potential that is still remaining on this channel, the potential that is still there. Vg minus Vx minus Vt. Area is for this infinitesimal region is W, the width of the device, times the delta x. Time we calculate is the time to transit this region, which is delta x over Vd. Vd is mu times c, low field regime we are talking about, and electric field in this region is simply given by the potential gradient. Rest we just reorganize the terms, integrate from 0 to L, that is the whole length of the transistor, and what we get is this expression. So this I don't have space here. Okay, we'll try to plot this. Let's just do one very simple thing. Let's put VDS is very small. Okay, and what I'll do is some typical values. Let's say Vg minus Vt is, let's say, 2 volts. Okay, and VDS is 0.1 volts. So 2 times 0.1 and 0.1 whole squared. So this second term will get neglected when VDS is very small. That's what you're seeing here. This square term that you're seeing will be significant enough only when VDS is high. So the expression which we are obtained in linear region, which was in the linear region, if you recall, only this much was the expression for linear. And the linear region, the approximation was VDS is very small. So if I put VDS very small, this term gets neglected. So this term that you see already incorporates the linear region expression. Okay, so what I'm from the competitive exam point of view, no need to remember the expression for linear region, just remember this expression. Okay, finally what we arrive at an event. So what you can simply imagine what happens if I keep increasing the VD, and the depletion region will keep on increasing and the inversion region will keep on shrinking. Assuming when I'm not changing VG, VGS and everything else remaining the same, if I keep on increasing the VD, this depletion region will keep on getting widened, and ultimately a point will come when the inversion layer will cease to exist on the drain side, right? That event or that VD is known as the state of the transistor is known as channel pinch off, because now you have pinched off the channel. The inversion layer is no more continuous. Okay, when does that happen? VDS is large enough such that the channel gets pinched off near the drain. So this will always be onset at the drain itself, right? We'll see what happens if we increase the voltage even further. Again, this was the expression that we had seen, Q inversion X. What is the extreme case? I say inversion layer is not even there. This means this is equal to 0. Cox can never be 0. So Vx, right? And I'm talking about the point at the extreme right. So that means the Vx, which is equal to VDS onset, let's say, will be equal to Vg minus Vt. This, what I'm calling as Vd onset, is also known as VDS sat. I'm explicitly calling it onset just to illustrate that when VDS you increase its value to Vg minus Vt, whatever it is for a given transistor, the channel will become pinched off. Okay, this is of primary importance. Okay, I had already written that here. So it become equal to 0, and Vx will become Vg equal to Vg minus Vt, which is called VDS sat or VDS sat. Okay, how to depict this? This is shown here. So this is left is your source again, right is your drain. So what we are happening is that at VDS, when becomes equal to Vg minus Vt, channel has become pinched off. You see the red region, the channel, the inversion layer has now ceased to exist. Nanometers, only a few nanometers, or even not that. So only just one small thin line will remain essential, and the depletion region you see has become so wide that it has completely encapsulated the whole charge there. So inversion charge does not exist anymore. Okay, now I have drawn another. So I'm calling this as I told you, VDS sat. So VDS sat is Vg minus Vt. What happens when you increase the bias, which is written in brown here, even further? Okay, When VDS is increased even further, but you are going to see this depletion region will now keep enhancing, this point will keep on moving to the left. Why? Because the depletion region will keep on expanding. Simple as that. So what you will see is that this will keep extending to the left. This happening on increasing VDS greater than VDS SAT. It will keep on shifting to the left, which I have shown over here. So you see the dashed line, the brown line, and below that will be your so in that case this will be the depletion region, even this will be the depletion region, everything this will be the depletion region. Okay, this means now we have even gone beyond pinch off. So this point that you see VDS1, now we have even gone beyond the pinch off. Okay, so again, if I try to, so if you see that this is what we are talking about, that the current, what it will be, Q inversion times area over tau. What you'll see is that I keep on saying that this inversion charge is not there anymore, so you'll say the current should reduce to 0. But I also said that the Kirchhoff's current law dictates that however many electrons are leaving from the source, in a steady state they must reach the drain. So what is happening? The thing is that the current transport mechanism after pinch off in this region is not due to the inversion charge. Okay, this I have written here. I'll write in brown, let's say, right? So I'll say the current transport, or rather not the current but the electron transport, in pinched off region is drift. In this region I'm talking about, this region, drift. Why? Once the electrons reach here, this is very similar to what we have in the reverse bias base collector junction. Okay, any electron which reached here was simply swept away by this high electric field. This electric field exists because, still remember, this is a depletion region. Depletion region means electric field is there, right? So whatever electrons will reach at this pinched off point, they'll simply be swept away and they'll reach the drain, and they'll from the drain, the circuit will be complete thereafter. Okay, so that's why the current transport in this, okay, when the inversion layer is there, it is dictated by this expression. After pinch off, it's dictated by just the drift, simply in this region. So that's why even if you increase the VDS, you will not see any increase in the current per se, because you're not changing, you are not able to change how many electrons are being injected from this side or how fast are they traveling. You're not able to dictate either the Q inversion or the tau. Area is anyways we cannot control by VDS, so both of these terms are out of our control, and hence the current does not increase, it saturates, right? And that's why you see these two curves. So again, we have already seen the linear region, right? I was not able to draw this in the previous slide. So these are the linear regions that you see over here. These are the regions that we had talked about using the gradual channel approximation, where we have the square term also coming, gradual channel approximation. And finally, after this point, what we have over here is the saturation. The current is flat even if you increase the VDS. So these are the three different regimes. So what we do is, typically we do not talk about, I will not say gradual channel approximation is a regime per se, but it's just the way, like we had depletion approximation for p-n junction. Similarly, we have this gradual channel approximation to understand the working of a MOSFET. So typically we have only two regimes, the linear regime and this the flat region, which is the saturation regime. Okay, the cutoff I'll draw in a bit. Okay, so let's just first solve this problem, and then I'll try to incorporate all the three regions in a consolidated place and with an expression of current. So in this question it's asked, a current source is a device which supplies a constant current irrespective of the voltage applied through it. So let's just try to see what they are trying to say. So they're saying this is some black box, so calling it as constant current source. Okay, what it does is that, and let's say this is a load. Constant current source is a device which supplies a constant current irrespective of the voltage applied across it. So let me call this, let's say this potential V load, and let's call this current I load. So what they're saying is that I load does not change with respect to V load. So whatever load you apply, the current will still be the same. Question asks, the long channel MOSFET, we have already talked about long channel MOSFET, not short channel yet, can be used as a current source in. Okay, one second. Okay, can be used as a current source in. So as we told, the load current does not change. So when we operate an N or a MOSFET in saturation, we had seen that when we operate a MOSFET in saturation, right, ID remains constant even on increasing VDS. We had seen that. This is what I had drawn. So this is VDS sat. This is ID versus your VDS. So this is what we had seen, and this is the regime that I'm talking about, saturation. This is the same problem statement as this. I load does not change, ID remains constant with respect to V load. So if you're changing V load, that means if you're changing VDS, nothing should change. So MOSFET in saturation, it means, so a long channel MOSFET can be used as a current source in saturation. Triode is essentially a linear, so this is cancelled, this is cancelled. In saturation, contributed by, I've told you, once we enter that regime over here, this is a depletion region only, and we have only the drift mechanism that is contributing. So what we have, the current is mainly contributed by drift mechanism of carrier transport. So this is the application of the device, of the MOSFET, for instance, in this case, where it's actually practically used. This is how it's used when you make a constant. There are other, I mean, it's not just only a MOSFET. There are other things to control the voltage and so on. So for instance, you want ideally VDS sat to be as low as possible, because remember, it's constant current source of saturation only after VD equal to VDS sat, greater than equal to VDS sat. So you want this voltage to be as low as possible, as simple as that. And ideally, you also want to support higher amounts of current, 1 amp, 2 amp, 10 amp, 20 amp. It's not, I mean, that's why there are more things, but there's more nuances to it. But the fundamental property that for a constant current source, MOSFET in saturation does satisfy the very basic condition to be used as a constant current source. Yes, there are other terms and conditions, so to speak, that VDS sat should be low enough or ID should be high enough and so on. Okay, so that's what we are, and the mechanism is drift mechanism. We had already talked about, since we have entered the depletion region and the strong electric field exists between the pinched off point and the drain, so the electrons can simply be swept away. Okay, fine. As I said, the whole picture that we had talked about, the three regimes, if you recall, right? First I had told was the cutoff, if you recall. So cutoff will lie, which is not drawn here, lies somewhere over here, the red line. But the current is essentially 0 because Vg is less than Vt. Vg is less than Vt, that is going to happen. No inversion layer is formed, no current will flow. Rather, very small amount of current will flow. So all the other curves that you see, they are Vg greater than Vt, right? That's what's happening. And as you are going up, if you're increasing VGS greater than VT, you are increasing VGS as you go up. This means you are essentially increasing the inversion charge, and consequently you see the current also going up. Okay, fine. Second point of interest is that when the device enters the saturation, we have seen that it enters at VGS minus VT after this point, and thus you see this parabola that is being drawn over here. This essentially comes from the fact that when you're increasing VG, right, so your VDS set will keep on shifting to the right, and just so happens that we enter at this parabola, and the linear regime is just so the region over here is not strictly linear, right? So when we want to operate in linear regime, we try to be as close to 0 VDS as possible, right? This is the linear regime, and this what we have over here is the saturation regime. As we had seen, saturation regime is important for a constant current source, right? The in-between regime is what happens in the device, but we usually tend to avoid it because it's difficult to, expression wise also, but there's a quadratic dependence here. Practically this is important because you have to take into account, but from numerical perspective, what we do is that we typically see the numericals we see encounter in the linear region and in the saturation region, and VDS sat is what I have already talked about. And the only expression that we need to remember is this. We had derived this using the gradual channel approximation. So from this expression, linear, I told you when VDS is less than VGT, let's say VDS is very small, so this second term will vanish. What we'll get is mu C ox W by L VG minus VT times VDS, right? For saturation, for instance, what's going to happen, VDS, we know it, this VDS will be replaced by VDS sat, VG minus VT. So you put this term here, you get C mu x W by L VG minus VT whole square by 2. So by 2 term comes because this becomes VG minus VT into VG minus VT, and this is also VG minus VT whole square. So that's half comes from that part. So this is the expression that is from saturation. This is ID sat. As I was saying in the earlier slides also, that it depends that this expression actually comes where we are talking about the temperature dependence of the drain current, right? So this is the expression that I was talking about in saturation. Okay, now based on the, we had talked about theory for quite a long time and some numericals also, some concepts also. Let's just try to solve some problems now. So we are given an ideal n-channel MOSFET with these parameters, so C ox, mu, and everything else is given. We are required to design the channel width. That means we need to find W, and we are given ID sat and VGS as these. Okay, so I told you this is the expression. When we are operating in saturation, I told you can simply replace VDS equal to VDS sat, which is VG minus VT. So we can write VG minus VT whole square by 2. Please note that in this problem VD is not given explicitly, but we are given the saturation current should be this much. Okay, let's put the values. So this is 5 into 10 to the power minus 3. Mu n is given 650. So now the units will be centimeters square. Please, we have to be careful. C ox 6 into 10 to the power minus 8. So the centimeter square gets cancelled. Very good. W by L. W is what we need to determine. L we know is 1 microns. So let's keep it 1 microns. So now the units have now changed to microns. Please remember this because centimeter square got cancelled. And half term VG minus VT. VG has been given to us as 5 volts. VT is 0.5. So 5 minus 0.5 whole square. From this we can get W as 5 into 10 to the power minus 3, 650 into 6 into 10 to the power minus 8, this 2 will come here, into 4.5 squared. Alright, so the numerator will come out to be 10 to the power minus 2. This will be 360. So this will be 3900 into 10 to the power minus 8 into 4.5 squared. So this will be 10 to the power 6, and then this will be 10 to the power 3 divided by 3.9 into 4.5 squared. I have just taken out the larger the 10, the powers of 10. So this becomes 10 to the power minus 2. 615 to 6 is 3900. 10 to the power minus 8 I retained. Then I made it 3.9 into 10 to the power minus 5. Okay, minus 5. So 5 minus 2 is 3. So that's what I've written here. Now let's find out 1000 divided by 3.9 divided by 4.5 divided by 4.5. So this is coming out to be 12.7. Alright, there's no such option like that. Okay, did I make some mistake? I think the answer might be wrong, because if you miss this factor of 2, then the answer comes out to be 6.3. I'll stick to this. I'll stick to my answer because I don't think I made a mistake. We are required to find. We are required to do this for a saturation region. So this is the correct expression. Yeah. So anyways, so these are. So this is how actually it's done. So because we require that what current we want, right? And we design. This is also a practice of design, that what VT you want, what VGS. But this is the L and WR is something when we are designing is under our control, more or less, and COX also for that matter, because please remember COX is TOX by epsilon ox by TOX. So what dielectric you are choosing, what is its thickness, COX is also you can control. So while designing, L, W, COX are the three more readily available parameters, I should say, because they depend on the lens, right, rather than on doping and whatnot. So these three are in our control, and other also like the doping of the substrate and so on. Okay. Now, as I was saying, that till this point of time, this is a 4-terminal device. This is a 4-terminal device. Please note that. So what we have is gate. This is your gate metal. This is your oxide. This is a semiconductor, and this is the body that I have been talking about, V body, and we have been saying this is to be. Let me draw this also. So you have source, which is grounded. This is source, and on this side you have drain, where you'll apply some potential, which will determine whether we are in linear saturation and whatnot. This body terminal that I've been saying, we usually short it with source, right? When I was talking about the depletion region, that's what I have argued. Sometimes we deliberately may choose not to do that. Okay, now the question arises, so why would you choose not to do that? Okay, the answer to that lies because it can affect VT, the threshold voltage. Let's just forget about in the numerical terms. Let's just see what happens when we apply a bias, any bias, to VB. Okay, what essentially is going to happen, it will impact the onset of inversion, so to speak. You can clearly see that if this also has some potential, let's say VB is, forget about source and drain, let's talk about MOS capacitor. Let's say and argue that V flat band is 0. Forget about this voltage as well. So when we apply a body potential of 1 volts and we apply gate potential of 1 volts, which means that you are still not effectively applied any potential, you are still at flat band, right? So by applying, and you have to apply higher potential on gate, right, in order to cause a depletion and then further to cause an inversion. That's where body terminal comes in handy, because just by using this term, okay, just by the use of this term, you can tweak with the threshold voltage of the device. How does it happen actually? So it's straightforward. This is the expression of the threshold voltage that we have. V flat band, as we know. 2 phi f is to denote the onset of strong inversion, which is the definition of threshold. And the next term that we have is basically coming from the depletion charge that we have. We know that is the depletion charge expression that is coming from. You have added another term to that. This is the potential essentially that we are applying at the bias. So when you apply let's say a negative potential, so to speak, you are forcing it to cross a higher threshold. Simple as that. And now all the other things are just the rearrangement of the terms. It's only the first expression is the one that I wanted to talk to you about. Okay. And because the other parameter called gamma, so what you see, you add and subtract these two terms. This gamma is essentially Vt naught is being determined when you have zero body bias. This is your standard without when body and source are shorted. So this is the Vt naught that is usually you see in your data sheets. This is the parameter that you can change, that is in your hands. So apart from while operating at, once you have fabricated that, now you cannot change the lens and doping, but what you can only change is Vg, Vd and also Vb. So Vb also is a good control because now you can change the threshold voltage. Okay, so sometimes you do it deliberately. So for instance, we know that in a circuit Vt has changed for whatever reason for one particular MOSFET, and we want it to during its use we want it to return to the original value, but we cannot fabricate this device again or break the circuit apart. What we do simply is we apply a suitable body bias, simple as that, and thus we can tune the threshold voltage. Okay, so based on this understanding, let's try to solve this problem. So we have an ideal n-channel MOSFET at 300 kelvins. The substrate doping, which will be accepted type because it's an NMOS, so the substrate should be P type, is 3 into 10 to the power 15, and we have a silicon dioxide thickness of 500 angstroms. 500 angstroms would mean 50 nanometers. Okay, and VBS is minus 12 volts. We are required to find the change in threshold voltage due to the applied source to body voltage. So we are required to find only the change in threshold voltage. Okay, that means only this term, because this is the standard threshold voltage without any body bias. Okay, so I can simply write that delta VTH will be equal to this gamma is actually this factor, so we'll write 2q Na epsilon silicon over Cox and 2 phi f plus VSB minus square root of 2 phi f. So let's see which terms we know. We know Na, we know epsilon, we don't know Cox, but we can calculate Cox. Let's do that first. So Cox will be so this is normalized by the way to area. So this will be epsilon ox and epsilon naught rather divided by Tox. Epsilon ox is given as 3.9, epsilon naught we know 8.85 10 to the power minus 14, and Tox is been given as 50 nanometers. 50 nanometers, we have to convert it to centimeters, so 50 into 10 to the power minus 7. Nanometers minus 9, so if converted to centimeters it will be minus 7. Okay, so this will come out to be, this will be 0.5, so I can write it 7.8 times 8.85. This will be minus 5, this will be minus 9. Okay, so 7.8 times 8.85, this is coming out to be around 6.9 into 10 to the power minus 8. Okay, the units would be farads per centimeter squared. 1 second. Farad per centimeter square is for epsilon naught, and like this. Fine. The next term is VSB is given to us as plus 1 volts. The next term we don't have information is 2 phi f, and phi f as we did in the last also, phi f, if you recall the expression, is basically the difference in the Fermi level from the intrinsic level in the bulk, right? How do we know that? We can simply say that P equal to Ni exponent of Ei minus EF over KT. This expression we had seen in the last session, as well as when we're talking about the intrinsic carrier concentration and we introduce the doping. So P we know, assuming 100% ionization, P will be nothing but your 3 into 10 to the power 15. Ni we know is 10 to, okay, it's given is 1.5. Ni has been given in the problem itself. It's 1.5 into 10 to the power 10 per centimeter cube, exponent of EI minus EF is, this will be your phi F over KT. Okay, 1 second. Yeah, so this is from here. What you can do is you can calculate phi F. So phi F will be your KT by Q. That depends on how you want to express phi F. If it's in volts, KT by Q will give you in millivolts, which we want essentially, because VSB has been given in volts. So this will be 26 millivolts, assuming at room temperature. Yeah, it's given 0.026 volts, and ln of whatever this number comes out to be. So it's 3, so it will be 2 into 10 to the power 5. So get this value of phi F, get this value of Cox, put over here, and you can see this will be a positive threshold shift because of the fact that we had applied a positive a negative body potential. So so we had talked about this, and again to re-emphasize, this is of practical application, just not for here. This is actually used to tune the threshold voltages in a circuit where we want, fabrication wise they're all the same, but you still want slightly different threshold voltages. This is a very effective way of doing that. All right. Now next, okay, I have a couple more questions and 4 to 5 minutes. I'll try to see if we can finish it off here, or otherwise we'll leave it for the next session. The two identical NMOS are given, and we want to use it as a switch in the linear region. So in the linear region, they're bisimilarly with only one difference. A uses Al2O3 while MOSFET B uses SiO2. So let me first write the expression for that. So mu Cox W by L Vg minus Vt. So they are the same. Both the transistors are the same. So their mu will be the same, right? Because it depends on the inversion layer mobility, so to speak, right? So this I'll assume is the same. W by L, it's given the same. Biasing is given the same. And Vt, if we see, Vt depends on V flat band, which again depends on your oxide trap charges. Again, I'm assuming them to be the same. And phi F, we know it depends on the doping. So doping also is remaining to be the same. So Vt is remain the same. The only thing, so I is a function of Cox, right? And Cox, if you know, is dependent on epsilon ox, area as well as thickness also, but those terms are the same because these transistors are the same effectively. So Cox will depend on epsilon oxide, and epsilon for aluminum oxide is something around 10. Okay, so I can say that Cox for MOSFET 1 will be greater than Cox of MOSFET 2. Why? Because epsilon ox 1, which is 10, and epsilon ox 2, which is SiO2, so that will be 4. So Cox of 1 will be greater than Cox of 2. Okay, so what does that mean? This will implies that ID of 1 will be greater than ID of 2, provided the biasing is the same, which is the same. So ID of 1 is ID of 2. Let's draw them. ID versus VDS. Again, we are interested only in the linear region. So let me draw this as ID1. So this is Al2O3, and let's draw in the dashed line SiO2. Okay, so we are drawing these two, Al2O3 and SiO2, and what we want is the on resistance. Okay, so on resistance, or on is written as is nothing but your delta VDS by delta IDS, essentially the inverse of slope of this curve, because this is IDS versus VDS. So I can write delta IDS over delta VDS. So you can clearly see the slope is higher for Al2O3, right? Slope is higher for Al2O3 as compared to SiO2. So this will give me R on for Al2O3 So this will be greater than, sorry, will be less than, slope is greater, right? For slope is greater, so R on value will be smaller. Delta IDS over delta VD is the slope. This is M1 and M2. M1 is higher, so 1 over M1 will be smaller. So R on for Al2O3 will be smaller than R on of SiO2, and that's what we want. We want a lower on resistance. That device is considered to be better. So we see switch with MOSFET A has lower on resistance. Okay. The last problem for today, we have these MOSFETs A and B. Okay, so overdrive voltage means VG minus VT. Okay. Alright, so what we are required to find is the transconductance. So ID, I'll just write again, mu and Cox, W by L, VGT VDS minus VDS whole square by 2. So del ID by del VG, this is the transconductance. Simply differentiate Cn mu x W by L. Okay, okay, let me, so this will be VDS, and yeah, so the rest of the term this will not contribute anything. Okay, so this is what we have, mu and Cox W by L into VDS. Just give me a second. I'll just confirm whether this is the correct expression. That I believe this is the correct expression. Yeah, mu and Cox by L Vg minus Vt. Okay, so or alternately you can also see that it's Vg minus Vt. Rather we should define it in the saturation region. That will be more correct, I would say. So I is mu Cox W by L Vg minus Vt whole squared by 2. So del ID by del Vg, this is the Gm. We differentiated mu Cox W by L. This is essentially x minus some constant k whole square. So this will be 2 times Vg minus Vt over 2. So this is what we get. So we get mu Cox W by L VGT. This is also known as the overdrive voltage, as I was saying. Okay. So MOSFET A is P-type MOSFET and MOSFET B is N-type MOSFET. Okay. So GMP will have, Cox is the same, W by L VGT is the same. So GMP will have, like equation to mu P, let's say some K time mu P, and GMN will be K times mu N. We know the mobility is higher for electrons as compared to holes. So GMN will be greater than equal to GMP. So transconductance for MOSFET B is N-type MOSFET, which has a higher transconductance. So that is all for today. GM is a transconductance, as I was saying. Conductance essentially current over voltage. Trans means from the other side. So the output current divided by the input voltage. That's what we mean by transconductance. Okay. There are other various parameters like output conductance, that will be delta ID over delta VDS. Okay. Input resistance would be your delta VGS over delta IGS. If it's an ideal MOSFET, it should be infinity, because we are assuming an ideal insulator, right? So that's all for today.